G'day, Dustin here. We are currently sailing, well, we're not sailing, we're motoring because there's no wind. We're motoring south along North Carolina's Outer Banks. We're about 5 nautical miles offshore at the moment. That's about 10 kilometers. Now this stretch of coastline is actually quite famous. Just back north of us here at the Kill Devil Dunes is where the Wright brothers launched the Wright Flyer, just south of Kitty Hawk. And near there, on a place called Roanoke Island, that was the site of the first attempt at an English colony in 1585. But to mariners, over the last 500 years, this stretch of coastline has been infamous. From the Chesapeake Bay down to about Southport, this stretch of coastline has claimed at least 2,500 ships. And marine archaeologists put that estimate as high as 5,000 potential shipwrecks in this area. Now, while all those stories might be fascinating, that's not what we're about. I want to look into the science that underpins what has become known as the graveyard of the Atlantic. The number of shipwrecks in an area is a function of two things: the number of ships that move through that area, and then secondly, the number of hazards that those ships face. And the Outer Banks of North Carolina has certainly had its fair share of both. So let's start with the traffic. Shipping along the US East Coast really began to increase when Europeans started exploring the Americas in earnest in the late 15th century. But the reason why the North Carolina coast became particularly busy was due to a major natural feature just off the coast here, specifically the Gulf Stream. The Gulf Stream starts out at the Florida Peninsula and sweeps its way up the US East Coast till it gets to about Cape Hatteras before it spears off towards Europe. It's one of the world's largest and fastest moving currents, getting along in some of the high flow regions at about 4 knots. That's 7.5 kilometers an hour. Now I know that seems rather paltry by land standards, but for many of these early sailing vessels and even certainly modern cruising vessels that get along at say 10 to 15 kilometers an hour, then this current presents a major boost to a vessel's speed if you're going with it, and a major impediment if you're going against it. As one Ponce de Leon found out in 1513 when he landed in Florida. Now he supposedly landed around Cape Canaveral area and then sailed south around the Florida Peninsula, and along the way the fleet ran into the Gulf Stream at various points. In an account of the voyage it is written, "The water ran so much there it had more force than the wind and did not permit the vessels to go forward, although they put out all sails." From then on, the Gulf Stream became professional knowledge to many mariners, especially those heading back to Europe. Vessels south of Cape Hatteras would catch the Gulf Stream north until it turned east, and then they'd catch the westerly winds and head across to Europe. And vessels to the north of Cape Hatteras would catch another current, the Labrador Current, which flows south from Greenland all the way down to Cape Hatteras. So this piece of coastline was like an on-ramp to a nautical superhighway to cross the Atlantic. But ironically, these currents that resulted in so many ships coming past this stretch of coastline are also key players in underpinning the hazards of this stretch of coastline. Reading through shipwreck reports, the two main hazards that ships faced along this stretch of coastline were first, shoals, which are shallow areas of water which ships can essentially run aground on, and second, storms, which can either sink a ship outright or push them onto shoals. And both of these hazards are underpinned by or exacerbated by the currents, particularly the Gulf Stream. So let's start with the weather, and the first thing that likely comes to mind are storms, and certainly this area loves to get a storm on. The two most hazardous types of storms, at least from a mariner's perspective in this area, are tropical cyclones and extratropical cyclones. Tropical cyclones are low-pressure weather systems that in the northern hemisphere have counterclockwise rotating wind fields. In the US, depending on the wind speed, they are commonly referred to as tropical depressions, tropical storms, or when the wind speeds maintain over 120 kilometers per hour, hurricanes. And the reason why tropical cyclones are particularly problematic for the North Carolina coast has to do with the prevailing winds, the shape of the coast, and then of course the Gulf Stream again. So let's look at some hurricane data. I'm going to drop a pin here at Cape Hatteras, and we're going to put our search area at 300 kilometers from the Cape. I picked 300 kilometers here because the average Atlantic hurricane has a radius of 250 kilometers. So we know that another 50 kilometers for the impact of ocean effects, basically. Now, as the name suggests, tropical cyclones form in the tropics and subtropics. If we look at Category 3 hurricanes, for instance, you'll see that they start out here essentially over the warm waters of the equatorial current, and then they travel in a east to west direction before getting near the southeastern side of the US, and then they turn north towards North Carolina and then eventually turn back out to sea. And as noted, the Gulf Stream also plays a part in the hurricane formation or intensity. So if we look at Hurricane Irene, for instance, Hurricane Irene developed down in the Caribbean Sea as a tropical depression before becoming a Category 1 hurricane just off the north coast of Cuba, and it continued to head north, crossing over the Florida Peninsula. As it moved off the coast here, the winds increased, and the reason for that was because it was being fueled by the Gulf Stream. This image shows the path of Hurricane Irene with the sea surface temperature data underneath it, and that red area is the Gulf Stream itself flowing up the coast of the US. So as Hurricane Irene travelled north along the coast of the US, the warm water and air from the Gulf Stream increased its intensity until it reached peak intensity just off the North Carolina coast as a Category 2 hurricane. When we throw all the track data onto the map at once, 297 storms of tropical storm strength or greater came through the North Carolina coast, and 134 of those were hurricanes of Category 1 or more. So an obvious question here is, how does this compare to other areas along the east coast of the US? So again, we can drop a pin near Brunswick, which is at the Georgia and Florida border. There are 229 records since the 1850s. And we can do the same thing for Miami. It has 220 records since the 17th century, hurricanes have caused at least 480 shipwrecks along North Carolina's coast. Extratropical cyclones, locally referred to as nor'easters or Hatteras lows, are also low-pressure weather systems that exhibit counterclockwise rotating wind fields in the northern hemisphere. However, they originate in the mid-latitudes, typically over land, and they also have strong frontal boundary systems associated with them. In the North Carolina region, they're particularly problematic because as they exit the coast, they then essentially become fueled by the warm air sitting above the Gulf Stream and can rapidly develop into a serious storm, generating winds in the order of 70 to 80 kilometers per hour and gusting in to the 100 kilometers per hour. Now, the problem for these old sailing vessels was that the prevailing winds in this area blow from the southwest through to the northeast, and these old vessels didn't have engines, or they can't sail into the wind like modern sailing boats can. So if a vessel was trying to head south around Cape Hatteras, they would have to wait on the northern banks essentially until the wind switched around to the north. The historian David Stick described the scene as following. There were sometimes as many as 75 or 80 ships just north of the Cape, and when the shift in wind finally did come, it was not uncommon for the newly arrived northerly winds to reach gale force before the first of these sailing ships could make their way around the Cape. The result frequently was shipwreck. One particularly devastating example occurred in 1889 when a low pressure system moved off the North Carolina coast, quickly gained intensity and developed into a strong nor'easter, and in one day 5 ships were sunk and 28 crew lost their lives. The final weather hazard that mariners face in the graveyard of the Atlantic is that of fog, and the currents are again key culprits in this. So as the Gulf Stream flows north, it brings with it obviously warm water, but also the air above it is warm and moist. And when that warm, moist air meets the cold air that's accompanying the Labrador current, the result can be thick fog. Of course, the big issue with the fog is that it becomes so dense that you can only see kind of tens of meters in front of you. And for old sailing vessels that don't have modern technology, then it's very easy for them to run ashore or run into another ship. And the Laura Barnes is a telling example. It was a 4-masted sailing ship that in 1921 entered into dense fog and essentially ran aground on Coquina Beach. Weather can of course cause shipwrecks directly, but they can also make ships run aground on shoals, and shoals were, on their own, one of the biggest hazards for the graveyard of the Atlantic. Looking at satellite imagery, we can see that the entire coast of North Carolina is comprised of sand. There are no rocky outcrops or headlands that are often seen in other places. And this makes for a particularly dynamic stretch of coast. This is a time lapse of Cape Hatteras from the mid-1980s until 2020. And from year to year, we see this constant change, which is just the sand being pushed around. And so shoals form along the North Carolina's coast due to all this moving sand, and they form in 2 main areas. First at capes, and then secondly at the inlets or mouths of rivers. When we look at the shipwreck distribution data, we see that about 40% of approximately 2,600 well-documented shipwrecks due to natural causes, so that's not including ships lost during wars or anything, 40% of that 2,600 occurs at inlets on shoals. Shoals occurring at inlets are more formally referred to as tidal deltas. Any inlet that's open to the ocean is going to be subject to tidal conditions. However, since the substrate or the bottom material in this region is essentially sand, as the tide water moves in and out, it's picking up some of that sand and moving it along with it. When the tide's going in, it forms what's referred to as a flood delta, and when the tide's going out, it forms what's referred to as a ebb delta. The flood and the ebb here just relate to the incoming or the outgoing tide. Now, interestingly, flood deltas are typically shallower than ebb deltas, and this is because longshore currents on the ocean side move some of that deposited sand away from the inlet mouth. Longshore currents refer to the movement of water along the coastline, parallel to the coastline, and they're generally caused by oceanic currents as well as wind and wave activity. North Carolina coast is primarily made up of barrier islands, and barrier islands themselves are comprised almost entirely of sand. And so the combination of that sand with tidal flow and these longshore currents means that inlets and their associated tidal deltas are highly dynamic structures that essentially creep along the coast in unpredictable ways. And one of the more famous ships to be lost at an inlet was that of the Queen Anne's Revenge. It was captained by Edward Teach, who went by the stage name of Blackbeard. Teach had captured the Queen Anne's Revenge from the French in 1717, who were using it as a slave ship. And then in 1718, he ran aground on the shoals just outside of Beaufort Inlet. The amazing thing about this was that the shipwreck was only discovered in the 1990s. And so if a vessel like that could go undiscovered for nearly 300 years, it's just amazing to think of the numerous ships that are forever lost to the graveyard of the Atlantic. Moving on to shoals at capes, which presented an equally treacherous hazard to these early mariners. They accounted for about 30% of all shipwrecks. The shoals at capes form because of these longshore currents I mentioned. When those sediment and currents reach a cape, essentially there's no shoreline left, and so those sediments get deposited into a depositional field off the end of the cape itself. Each of the three capes along North Carolina's coast have an associated shoal. These cape shoals are rather significant structures projecting from the coastline by tens of kilometres. They're perhaps several kilometres wide, and they change the depth from 12 to 15 metres beside the shoals to perhaps just a few metres on top of the shoal itself. Now, the geomorphology of these shoals is rather fascinating because the sand doesn't just get deposited in kind of one big mound. Instead, like the photos you see of deserts with the big rolling dunes, that's caused by wind. Here, underwater currents cause a similar feature across the shoals. To simulate this effect, I put some water and a bit of sand in the bottom of an esky, what Americans would call a cooler, and let it sit. Then the natural motion of the boat causes the water to move, which in turn pushes the sand around. The dominant movement of the water is along the long axis of the esky, and what we see is that the little sand dunes form perpendicular to this dominant movement. Shoals off the capes form similar patterns, however the ridges run northwest to southeast because the prevailing winds and current runs from southwest to northeast. Admittedly, the sand waves in the shoals are a little bit larger than my little model. They have wavelengths of approximately 300 metres and a wave height of about 8 metres. It's easy to imagine then these old sailing ships sailing up and down the coast with a draft of about 7 metres, so that's the depth of the boat under the waterline. And they'd be moving, say, 10 kilometres from shore, and when you're this far out, it's hard to see land. You have to basically be looking through binoculars to see it. So it's hard to imagine that the water would be so shallow there. They'd be checking the water depth all the time, dropping what's referred to as a lead line overboard, checking the depth. It would be, say, 12 to 15 metres deep, and then all of a sudden, whammo, you're on a bank. Of the three shoals, the Diamond Shoals claim more shipwrecks than the other two put together, and a big part of the reason for that was our little buddy, the Gulf Stream again. Other than the Florida Peninsula, the Gulf Stream makes its closest pass to the US East Coast right here off Cape Hatteras. And although it moves around, sometimes it's closer to shore, sometimes it's further out, the western wall of the Gulf Stream can be as close as, say, 15 kilometres from Cape Hatteras itself. That means it's basically flowing over the outside of the Diamond Shoals. And so this presents a major problem for all those vessels that are southbound. Essentially, they only have three options. First, they could head far offshore, avoid the shoals and also avoid the Gulf Stream. Second, sail sufficiently far offshore so that they miss the shoals, but then also fight the Gulf Stream, which might be flowing at say 4 or 5 kilometers per hour. Or number three, which was often the preferred option because it was the fastest, but it was also the riskiest. They'd try and shoot the gap. Essentially, they'd sail very close in to miss the Gulf Stream, but that would bring them very close to Diamond Shoals. And for these early vessels, which had low maneuverability and also a deep draft, it meant that any shift in the wrong direction could mean disaster. Southbound travel at the other capes just wasn't as hazardous simply because the boats could sail past the shoals while avoiding the Gulf Stream. Nevertheless, it wasn't only southbound vessels that the Diamond Shoals ensnared. One of the most mysterious shipwrecks of the graveyard of the Atlantic would have to be the Carolay Deering, a 255-foot, 5-masted sailing luxury cargo vessel. In 1921, it was heading north on its way back from the Caribbean, and the Coast Guard spotted it hard aground on the Diamond Shoals. They couldn't get to it for a few days due to the bad weather, but when they finally got aboard, they found that it had all its sails still up, and in the galley, food was being prepared. However, not a soul was on board. Well, none except a 6-toed cat, apparently. Now, what happened is unknown because the crew were never found. Perhaps they ran aground and then, fearing that the boat was going to break up and being so far from shore, decided to jump into the lifeboats. However, they might have got caught by the Gulf Stream and then swept out to sea. It's really a mystery, and for that, it's been referred to as the ghost ship of the graveyard of the Atlantic. Mariners still face the hazards of shifting sands and storms, fog, and of course the currents, but science and technology and even government services have greatly reduced those risks. For instance, now we have high-resolution bathymetry data, and so it's easy to see those areas that are potentially too shallow to transit through. There are of course some areas that don't have any mapping information, like the Diamond Shoals or various inlets, and that's because the sands are always shifting in those regions. At those places, however, we often find navigational buoys which mark out the channels of safe passage. Perhaps the greatest lifesaver has come from weather forecasting technology. The two best known weather forecasting models are that of the Global Forecasting System, which is developed by the US's National Weather Service, and then another weather model developed by the European Centre for Medium Range Weather Forecast, which is an independent intergovernmental organisation. And these models provide a pseudo crystal ball for what weather to expect in the short to medium term, say 2 days through to about a week. But the best thing of all is that all these forecasts, as well as real-time data such as wave action, what the wind is doing, where storms are, and even currents, can be accessed by anyone with nothing more than a cellular connection, or at worst a satellite connection. And then of course we come to boat level technology. Our boat is not particularly sophisticated, but we have on board a radar which allows us to spot incoming storms up to say 30 nautical miles, about let's say 60 kilometers away, as well as spot other ships that might be moving through at night or during foggy conditions. With all this technology, then it's unsurprising that one of the last shipwrecks to occur in the graveyard of the Atlantic occurred 40 years ago. It was a 100-foot fishing trawler named the Lewis Joyce. It ran aground at Oregon Inlet in 1981 during a storm. But of course, that is no reason for complacency. The power of nature is truly awesome and must always be respected.
Here it comes.